Hello, welcome back to the series where I show you how to do basic quantum mechanics problems. And in this video, we're going to derive the energy of a quantum mechanical particle sitting in a one-dimensional infinite square well. Now that might sound complicated, but don't let it scare you off. It's actually really nice, and we're going to weave our way through a route that does not involve any calculus. This is one of the simplest and coolest little derivations that I learned during my undergrad in physics, and it's what some people refer to as a back-of-the-envelope derivation, in the sense that you could fit the whole thing in the space on the back of an envelope. I'll show you the whole derivation right there, so there's really not much to it, right? And we'll take our time, go through it, but that's really all I have planned for this video here. And if you learned something new, make sure to leave a like on this video. You can leave a comment if you have any questions, and this will set us up really nicely for the final part I have planned for this little quantum mechanics series, part 5, where we will derive the radius of a hydrogen atom. So that's what this is all working up to, and make sure to subscribe if you don't want to miss that final part. And without further ado, you can grab an envelope if you'd like, and let's jump into this derivation. All right, so as I mentioned at the start, we are looking at our particle, quantum mechanical particle, stuck in a one-dimensional infinite square well. So a one-dimensional box, if you can imagine a one-dimensional box that our particle cannot escape from, and it's got one length, L, to our box, or well, really. And what we need to imagine here are the different waveforms that our particle can take on here. So this is what we call the wave function of the particle, and that's related to the probability of finding our particle somewhere, some location along this distance L. And what's really important here, because this is an infinite square well, we are never going to find our particle outside of the box. And so all of those wave functions need to come to zero right at the edges. And so imagine something like a sine wave. And I'll draw some of these real quick here, but let's look at a very simple wave function that our particle might have, something like that. So let's say that is number 1. Now, that might not look quite like a wave there, but let's move on up, get actually a full cycle of a sine wave there. So that's our number 2 wave. And let's move on up. We're moving up in energy here, looking at these more complicated wave functions we'll get. Now this one's always a little tricky to draw. I'll do my best here. I'll take it, not terrible. Number 3. And we can keep going, right? So the next one would have like 2 of these guys in there, so on and so forth. Now, what we're interested in here is the wavelength of each of these, and that's what we'll be able to relate to the energy. So let's try and find a pattern. Let's quantify exactly what each wavelength here is, and they're all different. So for the first one, we don't even get a full wavelength. A wavelength is an up and a down, right? A peak and a trough. A full cycle is one wavelength. So we don't even get a full cycle there, right? If it were to continue going outside here, then we could think about the full up and down, and it would actually be exactly twice the length there, right? So you can imagine this guy like that, and then flip it upside down out here. Well, that's 1L upside down part, second L. So our wavelength of the first one there is just 2L. All right. Now this one's a little simpler to think about. It's just L, right? We get an up and a down. So wavelength number 2 there is L. Perfect. Move this light so maybe we can see better. So there we go. And then this third one here, well, that's one full wavelength, and then you get an extra bit there, right? So it's like you fit 3 wavelengths, well, not 3, but like 3 peaks or valleys in this range right there. So 2 of the 3 is 1 wavelength. So we can write that as 2/3 L. 2L over 3, right? 2/3 of that length. And we can keep on going, right? If we got to the 4th one, as I said before, we would get like 2 full cycles within that range. So that would be 4L over 2, or just L over 2, right? Half the length. So we can think about this pattern that we're getting here. Let's try and come up with an equation to really define what the wavelength will be as we go infinitely high, right? You can just keep going higher and higher ends, higher and higher energies, really. And so the pattern we're getting, well, let's think about it, right? You can pause the video if you want, see if you can recognize the pattern here. And the wavelength is always getting shorter with n, right? So the bigger the n, the smaller the wavelength. So we might want our n's in the denominator here, and it's always related to L as well. And so if you plug in 1n, what'll pop out that guy, 2n, what'll pop out that guy, so on and so forth. And our equation, at the end of the day, is going to be 2L over n, right? And you can start plugging in these numbers to double check that. So you plug in n equals 1, you get 2L, perfect. N equals 2, 2's cancel, just get L, perfect. And yeah, I'll just keep holding as you go up. So we recognized the pattern with that equation right there, and that'll tell us the wavelength for any n as we go up. So that should be a familiar concept, this idea of wavelength. We've been talking a lot about photons and light, and also de Broglie wavelengths, thinking about matter. And let's think of the equation that we used for de Broglie wavelength, because we're thinking of a particle inside this box. And the wavelength you can relate to momentum as h over the wavelength is equal to the momentum. And what we can do then is plug this guy into there, see what we get. This is all leading up to energy, as I said. We get 2L over n right there. And then we'll bring the n upstairs to get our momentum equation right here. So that'll give us nh over 2L. All right, so we'll remember that guy now. It's a little confusing with just trying to underline it is all. Having multiple fractions in there, but yeah, just underline. Now we want to get to energy, right? And let's say inside our infinite square well, there's no potential energy. It's all kinetic energy. So what we're going to do is say our total energy is all the kinetic energy, which you may recall from the first video, get 1/2 mv squared, classical non-relativistic kinetic energy. And there's another way we can write this to bring in the momentum. So if you remember also momentum in that video, that's just mv. And if you go to about the halfway point, I mentioned how this can be, for halfway point in part 1, I mentioned how this can be rewritten as momentum squared over 2m. So that step should make pretty good sense there. All right, well, we have momentum right there. What if we plug it in? Then we can get an equation for energy of our little particle in this infinite square well. Very good. So let's go ahead and do that. I might have some more space right here to do that. So we're just going to drop this guy down. NH over 2L. That's all squared, right? Then I'm going to divide out 2m. So this might be a big step of algebra next, but we're just going to move everything down here into the denominator, right? You can think about it as like taking this guy and multiplying 1 over 2m. So we're just going to take these guys, bring them to the denominator. Now it's important to remember we're squaring them, so we're going to square that 2. That's going to become 4. Multiply it by 2 again. And so that'll give us an 8 in the denominator. And that L squared, right? First we'll put M, then L squared. That's the denominator, very good. And then in the numerator, we get N squared and H squared. And that right there is our energy for the particle in this system. Awesome. All in one fairly small space, a little bit bigger than an envelope, but that's very satisfying, and it's actually pretty easy to memorize all this, and it's a useful tool. So next time you're at a dinner party, you can whip out the derivation of energy for a quantum mechanical particle in a one-dimensional infinite square well. Definitely won't bother anybody, So I hope that was useful. Congratulations for making it to the end of part 4. And as I said at the beginning, make sure to leave a comment if you have any questions, leave a like if you enjoyed the video or learned something new, and lastly, subscribe if you would like to see part 5, the finale of this little series where we will derive the radius of a hydrogen atom and maybe do a little sample problem with that. So that should be the exciting conclusion of all this, and hopefully all the hard work will pay off. So thank you for watching, and I'll see you there.